Every structure, scaffold, and crane that we inspect follows one rule: equilibrium. When an object isn't moving, all the forces acting on it are balanced. It's not magic, it's physics. The total force in every direction equals zero. That's why a block on the ground doesn't sink or fly away. The floor pushes up with the same strength gravity pulls down. For safety pros, this concept helps us predict what happens when those forces aren't balanced. In two dimensions, equilibrium means the sum of forces in both the x and y directions equals zero, and the sum of all moments equals 0 too. That's sigma f sub x equals 0, sigma f sub y equals 0, and sigma m equals 0. Every load, anchor, and brace you inspect follows this balance. The moment you lose it, tilt, buckle, or collapse follows. Understanding equilibrium helps you see danger before it happens. In physics and on the job site, cables are everywhere. Cranes, rigging, systems, suspension supports, all working quietly to hold massive loads in perfect balance. An ideal cable has no mass, and its tension stays constant from one end to the other. When a load hangs motionless, that means the forces acting through the cables are perfectly balanced, a state known as static equilibrium. Let's look at an example. Two cables support a 2,000-pound weight. Cable 1 pulls at a 30-degree angle and cable 2 at 45 degrees. Because the load isn't moving, all the forces in both directions must cancel each other out. Horizontally, the left and right pulls balance. T sub 1 cosine 30 degrees equals T sub 2 cosine 45 degrees. Vertically, the combined upward forces equal the weight pulling down. T sub 1 sine 30 degrees plus T sub 2 sine 45 degrees equals 2,000 pounds. Solving these equations gives us two tension values, about 1,464 pounds in cable 1 and 1,793 pounds in cable 2. The steeper cable carries more of the load, which is why angle and symmetry matter in every lifting or support system. Understanding how to break tension forces into their horizontal and vertical components isn't just a math skill, it's a workplace safety principle that helps predict load pass, prevent equipment failure, and ensure compliance with OSHA and engineering standards. Now that we've balanced forces in cables, let's move on to another tool that keeps work sites and machinery running smoothly: the pulley. A pulley is simply a wheel with a grooved rim that guides a rope or cable. It doesn't change the amount of force, it changes the direction. In an ideal setup, the pulley itself has no weight and no friction. It only redirects the tension in the line. If we suspend equal weights on both sides, the tension in each rope is the same, and the cable holding the pulley supports twice that force. That's 2F. This is the foundation behind cranes, hoist, and rigging systems used in field operations every day. In the field, understanding pulley systems helps you evaluate lift points and anchor loads safely. Whether you're calculating mechanical advantage or checking line tension before a lift, this same principle, balancing forces, keeps workers and equipment safe. For your OHST exam, remember, every static system must satisfy summation f of x equals 0 and summation f of y equals 0 Just like with cables, the pulley only redirects the tension, it doesn't reduce it. When a beam carries a load that spreads out instead of a single weight, that's called a distributed load. Instead of one point force, the weight acts along the entire surface, like wind across scaffolding or gravel on a chute. To analyze it, we replace that spread out weight with one single resultant force acting through its center, the centroid of the shape under the load curve. In this example, the beam carries a triangular load increasing from 0 to 5 kips per foot over 4 feet. The total load is the area of the triangle 1/2 the base times the height, so 10 kips in all. That single force acts 2/3 of the way from the small end, or 2.66 feet from the start of the load. Because the load begins 2 feet down the beam, the actual location of that resultant is at 4.66 feet. This gives us one clean number we can use in equilibrium equations. The summation f of x equals 0, summation f of y equals 0, summation m equals 0 to solve for reactions. Every moving object tells a story, and velocity is how we measure it. Average velocity is simply how far something travels over time. Total displacement divided by total time. Instantaneous velocity, though, is the motion in the moment, the speed and direction at one exact point. Think of it like your car's speedometer versus your trip average, same road different snapshots of motion. When acceleration stays constant, motion becomes predictable, and that's where the kinematic equations come in. We can find position, velocity, or time using simple relationships. Delta x equals 1/2 a t squared plus v sub I t. That means displacement or change in position equals 1/2 the acceleration times time squared plus the initial velocity times time. These aren't just numbers. They tell us how fast something accelerates, how far it goes, and how long it takes. From a crane lowering a load to a falling tool on site, understanding these equations keeps the physics and safety balanced. Acceleration is how fast something speeds up or slows down. It's the change in velocity over time. The formula looks like this. A equals v sub f minus v sub I divided by t sub f minus t sub I. In plain English, that means acceleration equals the change in velocity divided by the change in time. It tells us how much an object's speed changes every second, like when a crane starts lowering a load smoothly or truck brakes to a stop. And because acceleration has both size and direction, it's a vector, not just a number. Kinetic energy is motion in action. It's how much work something can do while it's moving. The formula is capital K, capital E, equals 1/2 mv squared. In plain English, that means kinetic energy equals half the mass times the square of the velocity. So if you double the speed, the energy doesn't just double, it quadruples. Now for potential energy. That's stored power waiting to be released. The formula is capital P, capital E equals mgh. In plain English, that means potential energy equals mass times gravity times height. When you lift a beam or a bucket, you're increasing its gravitational potential energy. And when you let it fall, that stored energy becomes kinetic. Every lift, drop, and roll in the field follows this same law of energy transfer. Energy is never lost. It just changes form. Mechanical energy can turn into electrical, sound, or heat. Think about a car. Chemical energy in the fuel becomes mechanical energy as it moves. That motion creates friction, which turns some of that energy into heat. The same happens on a job site, a crane motor, a power drill, or even the heat off a braking truck. All examples of energy conversion. In every process, some energy escapes as heat. So the goal in safety and efficiency is to manage where that energy goes. Now let's talk about friction, the invisible force that resists motion. When an object rests, static friction holds it in place. Push harder, and once it starts to move, kinetic friction takes over, and that's usually smaller. For rolling objects like pipes or cable reels, we get rolling friction, which is even less. That's why wheels make moving heavy loads so much easier. On the OHST exam, remember, static friction prevents motion, kinetic friction resists motion, and rolling friction reduces effort. Every day on the job, physics is quietly shaping what we do. Every lift, every stop, every load in motion. Understanding these forces isn't just about equations, it's about safety, control, and prevention. When you see energy, motion, or balance in your work, you're seeing physics in action. And when you understand it, you're not just working safely, you're leading safely.